This video is part of an online course of Calculus 1, and I'm gonna talk about the situations when we need something else, when the limit laws are not enough to just calculate the limit of a function. Okay, let me start. If the function f of x is defined on an open interval containing the point A, then we can actually use limit laws to evaluate the limit of f of x as x goes to a. Okay, since the function f is defined on an open interval containing a. Okay, the next situation is this. If a is an actually endpoint of the domain of the function f, what it means this: f is actually not defined on an open interval containing a. Okay, so what is the situation? The situation is this: I have the point A, and then the rest of the domain. So the point A is basically an endpoint of the domain of f. Okay, then in that case, this we can use actually the side limit. So then we have side limit, and we can use the graph of the function and also the limit laws to evaluate this limit. Okay, let me have one example, like the limit of square root of x as x goes to 0. As you know, a square root of x is this function. Is like this: y equals to square root of x. At the point 0, we don't have the left hand side of 0 as in the domain, so the point 0 is basically the beginning of the domain of the function. So this limit, actually, when we have on the left hand side, it does not exist. Okay, how about the limit on the right hand side? I can use the graph, and looking at the graph is if x is getting closer to 0, the function is getting closer to 0. And also I can use the limit laws in here, and then it's equal to that, it's equal to 0. Okay, because it would be square root of 0, which is equal to 0. Very good. So when we have the endpoint, a is an endpoint, then when we take the limit of the function as x getting closer to a, we need to pay attention that on one side the limit does not exist, on the other side we can use the limit laws. Okay, now another situation that we have is this one. If actually the point a is not on the domain of the function f. Okay, what is the situation? The situation is like this. So we have the point A, and we basically have a hole. This is the function f. We basically have a hole at the point A. It is not in the domain. Let's look at one example. For example, we've been asked to find the limit of x squared plus 1 divided by x minus 1 as x goes to 1. As you see, x equals to 1 is not on the domain of this rational function because it makes the denominator 0. It is not on the domain. Okay, so what is the strategy to find the limit here? So in this situation, we have a couple of strategies. Strategy 1 is this. Strategy 1 is that when we calculate the limit, we get a number over 0. How do we get that? Well, we say that it's the limit of f of x divided by g of x as x goes to a, and as I said, a makes g of x equals to 0. So when we calculate the limit, we get a number over 0, where the number L is actually the limit of f of x as x goes to a, and it's equal to L, and the limit of the denominator as x equals to a is equal to 0. That's a problem that we have in here. Okay. There are some details in here, and the details is that if the limit of f of x as x goes to a is a number and the number is positive, and the limit of g of x as x goes to a is 0 positive. What do I mean by this? By 0 positive, I mean that the function g of x approaches to 0 positively. It means that for some numbers that are greater than 0. So I can say that it approaches to 0 positively. Okay, so if we have this situation, we get the limit of f of x over g of x as x goes to 0. We get a number L which is positive, and we get 0 on the denominator, but from some numbers that are greater than 0. I have a positive number in here, a positive number in here, which is so close to 0. That's why we get positive infinity. The second situation is that we have the same thing, and the limit of g of x as x goes to a, it's 0 negative, which means that it approaches to 0 negatively, so with some numbers that are greater than, that are less than 0. Then we get the limit of f of x over g of x as x goes to 0 as L positive and 0 negative, which means that we're getting closer to 0, but from some numbers that are less than 0. So positive number in here, negative number in here, together I get negative infinity. Let me give you a note. All of these situations, situations 1 and 2, all above, they hold for x goes to a from right hand side or x goes to a from the left hand side when we have the side limit and these situations. Let me have just an example and then you will see. So what is the limit of x squared plus 1 over x minus 1 as x goes to 0? I'm sorry, x goes to 1 actually. Okay, so when x goes to 1, I get the number 2 on the numerator and 0 on the denominator, which means that this limit does not exist. But we can specify. Let's see. We have side limits. If x goes to 1 from right hand side, then we get 2, but x is getting closer to 1 with some numbers greater than 1. For example, we get 1.5. It's getting closer to 1 from numbers that are greater than 1. So I get 1.5 minus 1, which is 0.5. So I get 0 positive in here. So 2 is the number positive. I get 0 positively. So it is positive infinity. Okay. What is the limit of x squared plus 1 over x minus 1 as x goes to 1 from left hand side? This here, it means that we are getting closer to 1 from numbers that are less than 1. So for example, 0.9. Okay, so I get a 2 and here a numerator, and on the denominator just plug in 1, so I get 0. But we are getting closer to 1 from the left hand side, which means from some numbers less than 1, like 0.9. So 0.9 minus 1 would be negative 0.1. So we're getting closer to 0 with some numbers that are less than 0 with negative. So positive over negative, I get negative infinity. Okay, so that was strategy 1, to have a number over 0. What if we get 0 over 0? So that would be a strategy 2. So strategy 2, okay, when we get 0 over 0. Let's see. If the limit of the numerator as x goes to a is equal to 0, and the limit of the denominator as x goes to a is equal to 0, we're gonna try to basically simplify the whole fraction, and then we're gonna use limit laws. Okay, what are the basic simplification that we can use? I'm gonna say just 2 of them for now. For example, when we have f and g like polynomial, we're gonna factor out, if we can actually factor out, and then we are gonna cancel the common factors from top and bottom, from here and here. And if we basically cancel out some common factors, then we won't get 0 over 0, and our expression is getting actually simpler. Or the second strategy, if f and g are they contain some expression with square root, then we're gonna multiply f and g by the conjugate of the expression. And sometimes when we multiply it by the conjugate, then it's getting simplified. And then there are some other strategy that you're gonna see on the examples. Okay, that's good. These are the method for simplification. And let me give you a fact. And the fact is that if we have 2 functions, h of x and k of x, for everything except just one point, for everywhere except just one point, then the limit of these 2 are equal to each other when x is getting closer to the point A. So this is the idea behind simplification. Since we simplify a function, we get the function that is equal to this, so their limit would be the same. Let me have some simple examples like this. What is the limit of x squared over x as x goes to 0? Well, you see, if I plug in 0 over here, I get 0 over 0. This is the subject for strategy 2. That's why I need to simplify that. When I simplify this x and one of these x is going to be cancelled, and I get 0. Okay, another example. The limit of 2x over x as x goes to 0. You see, plug in 0, I get 0 over 0. Simplify that, I get the limit of 2 as x goes to 0, the constant function. I just get 2. Okay, then another example, x over x squared when x goes to 0. I get 0 over 0. Simplify that, I get the limit of 1 over x as x goes to 0. So this is what? This is 1 over 0, which basically infinity. This limit does not exist. This is infinity, right? If x is getting 0 from the right hand side, I get positive infinity actually, or left hand side negative infinity. So this limit does not exist. So as you see, based on these 3 examples, anything can happen when we get 0 over 0. Anything can happen when we get 0 over 0. After our simplification, we can get anything. Like we can get does not exist. If we have the side limit in here, it will be positive or negative infinity. We get some numbers, so anything can happen. Let me have another example in here. Example, what is the limit of square root of x plus 2 minus 1 over x plus 1 as x goes to negative 1? Plug in negative 1 in here, I get 1 minus 1, which is 0 divided by 0. Okay, so I need to simplify that. I have my expression with square root. That's why I'm gonna multiply it by the conjugate. So the conjugate would be x plus 2 plus 1 over the same thing, x plus 2 plus 1. When I multiply this by this expression, because top and bottom they cancel out, it means that I just multiply everything by just 1, okay, which is nothing. So what do I get? I have something minus 1, something plus 1. So it would be that something square and then minus 1 square. That's the idea. A minus b times a plus b would be a squared minus b squared. That's how I get this. Over x plus 1 and then x plus 2 plus 1. Okay, and then x goes to negative 1. Okay, let me simplify that a little bit. I get what? X plus 1 on top, x plus 1 on the bottom, and then x plus 2 plus 1 as x goes to negative 1. This and that would be cancelled. I get 1 divided by plugging negative 1 into here. I get a 2. And as you see, 1 over 2 is the answer for this limit instead of 0 over 0. I just multiply it by the conjugate and I simplify that. Okay, so this is the second strategy that we need to use. Basically, when we get 0 over 0, we need to simplify that by factoring it out or by multiplying by the conjugate. The third strategy would be using a Squeeze theorem, which I'm gonna explain it in the next video.